Good afternoon, everyone, and welcome to the first in a series of optimization webinars that we'll be holding here using our Palisade products, in particular Evolver and Risk Optimizer. This is part one, where we'll be focusing on Evolver, getting you up to speed with some of the fundamentals of optimization in a spreadsheet, what that all means, and also some ideas on how to utilize the software to help optimize your own models. As always, we'll be recording this webinar, so if you do miss any of it or you'd like to see it again later, the recording will be put on our website shortly after we finish the webinar today. Pardon me. And also, as you'll know from previous webinars, due to this format, I won't be able to respond to questions during the broadcast itself. However, if you do type down a question or indeed contact our office at any later point, we'll endeavour to answer those questions for you. So let's get started. You can see on the screen in front of you is my Excel, and I have Evolver already launched, ready to go. There are only a handful of buttons in Evolver because for the most part, optimization work is done by the user. If you like, the difficult part of optimization is the construction of a set of levers that enable you to change the value of a decision that you can make, or multiple decisions, and see what effect that would have on your organization. In other words, build a spreadsheet model with decisions built into it. Now, Evolver, pardon me, our fabulous optimization engine, does not build models for you. It does not determine a specific optimization type, such as a linear program structure. It, just as at-risk does, enables you to solve or optimize problems of any type, anything that you can conceive of or put into the spreadsheet. So one thing that we'll notice as we go through these, pardon me, through the models that we'll look at today, they could all be quite different. They'll all be in different areas, different industries. And, pardon me, the key is that the building of such a model is entirely up to you. So there is no such thing as Evolver for logistics or Evolver for budgeting. There is just Evolver, sits inside Excel, enables you to build models, and then find out what is the optimal solution for you in terms of the decisions that you can make. You can see I have the Evolver example spreadsheet open with various examples in here. For the most part, I will be sticking to these examples over the next couple of webcasts. That'll enable you to look at these yourselves later, pardon me, and follow along as needed, or as you would like. So let's get started. Let's talk about optimization, what it is and what does it mean. Simply put, we are looking at making decisions and making the best decision that we can. Now, a decision could be a simple matter of a single variable of which we need to know what is the exact best amount to use or spend or produce that helps optimize our outcome. One example might be, what is the optimal sales price for a product that maximizes profit? So if we charge a lot, our per unit revenue will be high, but our demand will be lower. If we charge too little, although our demand is high, our per unit revenue goes down. So somewhere in between, probably, will be the optimal sales price. Now that sort of thing might sound like it's not too difficult to do if you understand the relationship between price and demand, and perhaps between price and, pardon me, just the relationship between price and demand in that case. You might be able to work out what is the best or reasonably good sales price for you. However, what if we also threw in the idea that along with sales price, you could potentially adjust your production levels? If you produce only a small amount, there's less chance that you will have surplus stock left over. However, obviously it limits the amount of revenue you can generate. And it will also increase your per unit cost. if you produce a lot, your per unit cost goes down, but then you also run the risk of severely overproducing, not selling enough, and therefore maybe even losing money. Each additional decision that you can make increases by that factor the number of possible decisions you could actually make. Are there thousands of different decisions you could make? Hundreds of thousands? Millions? Billions? If you had $1 million, how many ways are there to invest that? It's practically unlimited. So what we need to do is have a structure that works out, if I make a particular decision, here is the outcome, and then an algorithm or algorithms that take that structure, take the rules you give it, such as constraints upon the total amount that you can spend, the maximum resources you have for producing particular goods, limits on the demand, minimum demand that you need to meet for certain products, maximum storage capacity and so on, takes all of that information, and these algorithms will therefore then at the end of an optimization run spit out the optimal solution. That algorithm or set of algorithms is a Volver. That's precisely what it does. Some of you may be familiar with the built-in solver in Excel, which is doing a very similar thing. However, solver has a lot of limitations. There are limitations on the size of the problem you can look at. There are limitations on the model structure itself in terms of how non-linear, lumpy and jumpy the solution space can be, and so forth. So what a Volver does is extend the basic idea behind solver to make it now flexible enough to solve any problem that you can possibly conceive of. And by conceive of, I mean build a spreadsheet model for it. Now let's just start with an example, enough talking to a relatively blank screen. I'm going to open the example file called transportation. Now in the transportation model itself, just a quick word, just like all of our example models, if you aren't familiar with them, they have an explanation sheet, which especially for the optimization problems really helps you understand what's going on. If we look at the model itself, we may struggle to work out exactly what's happening at first. So here's a simple little model. In transportation model, we have our, these might be factories or wholesalers, something where the goods need to come from, and then places we need to take those goods to. Easy enough. If I ship everything from my South Carolina plant, as you can tell obviously there's a North American bent to some of these examples. If I ship everything from South Carolina to San Francisco, Denver and Chicago, which is where they need to go, I can send 180 to San Francisco, which is the minimum demand there, 80 to Denver, and 200 to Chicago. So that meets all of my minimum requirements to get my goods to those three cities. My South Carolina plant is also the largest one, so it has more than enough capacity to handle shipping out 460 units. Now the trick in this model is that, or one trick, is that when I ship these goods, I don't ship them as a unit, they actually get shipped in trucks. Each truck can carry 6 units. So if I use 80 units, or send 80 units from South Carolina to Denver, how many trucks do I need? Well, this initially fancy-looking formula, but it's not really, lets me know that if the number of units that I ship is divisible by 6, then I know exactly how many trucks I need. Each truck is full. However, in this case, I could ship up 84 units, and I would still only be using 14 trucks, and therefore only incurring the cost of an individual truck. The extra unit going up to 85 units, now I need 15 trucks. Okay, so there is a little bit of a trick in here where it's not as straightforward as simply looking at the unit cost to ship. I have trucks to consider, and then I also have different shipping costs depending on where I'm going to and from. Now, why don't I just get everything to go through or from Arizona? Well, it's not the cheapest to Chicago, it's the cheapest to San Francisco and Denver. And well, Tennessee is the cheapest to Chicago. However, these smaller plants don't have the capacity necessary to meet my overall demand. So you can see, even in this very simple model, which is mainly an example of how to pardon me, set up a simple model, we can see that the number of permutations possible is enormous. So we absolutely do need an algorithm to help solve this problem for us. Now, if I say that I can just press ahead and try and reduce my shipping costs, let's go, I'll take some units from Tennessee instead. Maybe I'll put 100 there and only 100 here. And my overall shipping cost was over 30,000 before. It's now down to 29. So I've saved some money. So manually, I've been able to adjust where I take some of these things from to reduce my costs. Now, what if I take some units from here, 100 from there? So Arizona to San Francisco, so far so good. I'm sending more than I need to, so I'll make that only 80. Everything's still satisfied. 23,000. Okay, so it's getting better. But how many different combinations are or do there exist within this little grid of 9? A lot more than I want to go through and type in individual units there. Okay? So I'll go back to my starting point, which I know is not optimal because I was able to find a better solution that still maintained these constraints. And I'll get Evolver to solve this for me. So how do we do that? The first thing is we build the model. Okay? I have some simple functions to work out what is my the total number of units shipped to each city, and I know what the limit needs to be. It needs to be at least this much. Simple sum functions again to work out how much is being sent from each plant, and I know what each plant's capacity is. I know how many trucks are used by using this elegant but not too complicated function to work out exactly how many trucks are required for this many goods. And then the total cost is simply the sum product of the number of trucks I needed multiplied by the unit cost of each truck, depending on where I'm going to and from. So it's actually quite straightforward, a classic, simple logistics problem. How do I then optimize this? Well, once I've built that model, and you'll note that there were no at-risk functions or any other special functions in the spreadsheet, all Excel. Then Evolver, I define my model. And what does defining a model mean? Well, I have to decide whether I want to minimize or maximize my output cell, or indeed try and achieve a target value. We're minimizing cost here, so we're minimizing C26, total shipping cost. And how do we do that? Well, here is where I mentioned the word levers before. It's just another way of saying decision cells. Here I have these cells C10 to E12, which represent the number of units I will ship from each location to the destination, those 9 cells. I can only ship entire units of things. I can't chop these things in half. So not only is there an obvious limit of 0 is the smallest amount that I can ship, and arbitrarily I've chosen 1,000 as being the largest. None of these cells could actually exceed 800, let alone 1,000, but I've taken it out to 1,000. But I also want them to be integers. So Evolver enables you to do both continuous solution and integer solution, and also, one that we'll show in more detail later, discrete step size solutions as well. Again, this is another way in which Evolver is far more advanced than things like Solver. So integers for these 9 cells, but then I have 2 constraints that I wish to have satisfied. The first, pardon me, is the capacity constraint. So the actual number of units that I ship from each of my 3 plants, South Carolina, Tennessee and Arizona, cannot exceed their own capacities. And I have simple cell range constraints in here, and the decision that the total used or the total required from each location must be less than or equal to, out of the choices that I have, the capacity. Very straightforward, very logical, simple to include. Similarly, there's a limit on the demand. The demands must be met. If I go over demand, that's fine, but I cannot go or send less than this amount. A more complex optimization model might allow me to send less than what I've promised, but maybe there's a penalty involved. And it might work out that it's just dearer to send one extra truck than it is to pay the penalty, depending on how much that this constraint is violated by. So we can also include any sort of constraint that you can conceive of, we can include in the modeling. Now, how is Evolver actually going to solve this problem for us? I go to the settings option, and I start with the runtime. How long do I want an optimization to think for? Now, some types of problems, such as linear programming problems that we'll look at later, have a defined solution time. Mathematically, we know how long it will take. But the more complicated a model gets, the less we know about its runtime. So we can have an optimization run until we feel like stopping it, and now I have all of my optimization runtime options turned off. We could run it for a certain amount of time. We could run until a particular formula is true on our spreadsheet. We could run for a certain number of trials, as in a certain number of guesses, if you like, educated guesses that Evolver will make. The most common stopping regimen, however, will be for progress. So in this case, it says Evolver will be deemed to be stopped, as in it's found a global optimal solution to your problem, if for the last 20,000 attempts it has not been able to improve your solution by more than 1/100%. These, of course, are arbitrary. You might make this easier or harder to achieve, and fewer or even more trials to have achieved that. But these are the base settings, and that's pretty strict. That's pretty good. So that's what it's going to, or how it's going to end. What's it going to do during an optimization? Well, I need to choose an engine. An engine simply represents a different algorithm that enables Evolver to actually produce for us an optimal solution. Now, you can have optimization set to automatic, which means Evolver will automatically choose between the built-in genetic algorithm or the OptQuest engine, which includes these cool-sounding things: taboo search, scatter search, integer programming, neural networks, and I believe there may be some other elements to it as well, into a very cool optimization algorithm. Now, in latter webcasts, we'll explore what these things are and certain times where you may choose one over the other. When you're first starting, though, it's probably safer to let Evolver decide. Okay. Now, we used to only have the genetic algorithm included, which is a very powerful solver that, or solving algorithm that can really solve anything, but there are certain types of problem that are more efficiently solved with something else. In that case, OptQuest might be the best. But as I said, we'll discuss that in more detail in a later webcast, but for now, I'm just going to use automatic and let the software look at my model, look at the types of constraints there are, look at the optimization, the cell to optimize and so on, and let it determine what is the best algorithm to use. Okay. And then all I have to do is start. So Evolver is going to change the decisions in here. Pardon me. It's just preparing the model. It's going to change the decisions in here to produce a better solution. And we should be able to see the value strength and better answers on the spreadsheet. As we saw for those with a couple of weeks ago, due to running cast same time, the software was very slow, unfortunately. While on a webcast, I'll look for you if you're doing this. So we got for a while, it's suddenly came much better solution. So we went from 30,000 total to around 20,000 in a one big jump. That's the name of optimization. Generally, your improvements are made, and then the improvements will take off. Then maybe a good solution will be found. Maybe another one, but generally an exponential decline if you like in terms, and eventually big gains will be made. And at the screen now, you can see that despite going from South Carolina to Chicago is a dear way to get to Chicago. It's still using all too needed Chicago from South Carolina, because the algorithm has determined that it's actually more effective to use South Carolina to that than you can get Tennessee owners who go to San Francisco and Denver rather than using Chicago. Kind of makes sense what this good thing should be intuitive, but I wouldn't have there and come up with this solution anytime soon. I'm going to stop this optimization there. There may be something better in the model. I could let it run for longer. Obviously, it hasn't run for very long at all, only a matter of minutes, and only less than 200 trials in total. But I think I've got a pretty good solution at the moment, and I'll just stop that there. A quick word on run times. In general, Evolver should be able to solve even the biggest problem that you've got probably within half an hour. That's for a very big problem. You'll see some of the models that we'll look at later will be solved within seconds. But in general, I can't promise you what the run times will be. But it's certainly not a matter of days and weeks. The scale of a problem that would take that long to solve is quite mind-boggling. But here, I've just saved $10,000, in fact, a third, so about 30% or so, of my transportation costs, still getting exactly the amount of demand that's required without having to go over, not exceeding capacity for any of my plants, and then with an optimal solution. Okay, so that's optimization in a nutshell. Doing something that we can't do by hand, very rapidly, very intelligently. Now that transportation problem, sorry, I just want to show you one more thing about that. I was a bit itchy on my shutdown finger. These values here, my decisions, could all be changed independently. Eventually I might violate some constraints, but I can change this 180 here to any number, and these can change to any number, and they don't have to add up to 180. It's convenient if they do, but if they go over, there's no problem. Essentially, these 9 cells can all be varied independently. There is no direct relationship between them. However, there's another type of problem where there are definite relationships between those decision variables. So you can see here it says recipe examples. The problem we just looked at, transportation, is a recipe problem where the decisions can be varied independently. Now we're going to look at the second most common type of optimization, which is a budget problem where, as the name implies, we have a specific budget that we need to work to. Possibly the optimal solution won't use all of the budget, but probably not. We probably are going to use exactly 100% of our money or allocation to find the best model that we can. And this is one such example. Here I have a business model. Again, very small, but that's the idea is that it'll sit in one screen for you to look at everything simultaneously. And the question is, if I have $5 million and I need to spend it on advertising, marketing, production, salary, and operations, how can I maximize my profit? Well, I've put in some initial numbers for spends right now. So I've put $1,000 into production, full $2,000 on salary, all the money into operations, minimum spend on marketing, somewhere in the lower end for advertising, and so on. Now, all of these expenses have an impact on my business in different ways. So the marginal cost of production is affected by salaries and operations. Obviously, if I spend more on those areas, I should reduce the marginal cost per unit in my business. Capacity will be related to how much I spend on production. The ad saturation in advertising spend, and therefore the ad multiplier, affects my demand. So too does my marketing spend. So advertising and marketing both should have a positive influence on the actual demand for the product. Okay. Note here that I have a fixed sales price. That could also be potentially included as a decision variable. But then I have some straightforward calculations here to return my overall profit. Now this current spend, my $5 million spent in this way, has me losing $2 million. That's not a good return on the on my money. So instead, pardon me, instead what I want to do is change my allocation to improve my profit. But at any point, I always want to be spending exactly $5 million. Now, even worse than the transportation example, this becomes almost impossible for me to do by hand. If I spend 100 more in marketing, I need to take 100 off from somewhere else. So maybe 9,950 there and 1,950 down there. So I've got my 5 million spent again, and that's another option, and it's better than what I had before, but you can see how laborious it would be to actually go through that ourselves. So instead we get the software to do it. If I go back into my evolved model, we see that it looks the same, and it vary our spend on these things to be between the business determined lower and upper limits for each of those things. It could also be an actual limit where perhaps we simply can't spend more than 2,000 in production for whatever reason, or 1,200 on operations, that type of thing. But this is named as a budget type. If I edit this group, you can see that there are budget types, different solving methods. Budget, recipe was the one we saw before, and in our second webcast we'll explore schedule, project, order and grouping. We're starting with the most common, which are budget and recipe. So this is a budget problem. Now what Evolver will then do is whatever value these decision cells add up to when you click start, it will absolutely maintain that. It will never deviate from that as a sum. If it adds to something, it'll take away from some collection of the others, not in a simplistic way like I did where I added 100 to one and then took 50 off to others. It is smart enough to know that it can change any of them as long as it maintains this sum. Very clever stuff. There are no other constraints. All the constraints in this model are built into the limitations on the actual spend on each budget line. So if I look at my model again, similar issue around the progress. We're not going to run 20,000 plus trials, but I'll just get the software to try and make me some money. I was able to go from minus 1,000 to minus 1,300. Let's see if I can actually start to make some money. What are you making now? 2,500. Now to 7,000. So I was losing 2 million before. I'm now making 7 million. That's a pretty improvement. You can see I've done so by using the same amount of money. Now 7,000, 7.5, approaching 10. That's $10 million, which certainly looks feels a lot better than the $2 million loss previously. Oh, cleared through 10 now, 10.4. Just by changing things around. So we have a fixed budget. You say, what's the best way to spend this money? We have clients who utilize this for portfolio optimization. Obviously, there's a certain amount of money in the portfolio, and they invest in assets. And then they say, well, for this fixed amount of money, what's the best return I can get? And the lever they put is what portion of their money goes a week. So it adds up to 100. I might have money that I spend on projects, maybe a portfolio of projects. Which ones do I invest in? I have dozens, scores, maybe hundreds of options. What do I invest in with my money? So I spend on money, maximize my return, but I allocate it to 20. Now, I probably still have some potential gains here. I'll just stop that. You can see that we've already improved considerably. Obviously, if this was my organization, I'd run this for more than just 2 minutes. But we can see same amount of money spent, massive improvement. I can see that the spend on advertising and marketing has gone up considerably. Production stayed about the same. Operations and salaries a little bit lower. Okay? But for the same amount of money, I'm now making heaps compared to losing lots of money. The key with this example was that it is a budget example. I need to add these up always to equal $5 million. Now, in case you're wondering, can I go back to my original solution? I can reset this back to showing the original values. Just quickly do that. There we go. So what I'd like to do as well, I don't know if the price, I'm going to quickly check. Price goes into those things. However, I was wondering if price would influence demand. Unfortunately, it doesn't. If price impacted demand, I could also have Evolver determine simultaneously not just the best spend on these things, but the optimal price. Now, that's two different sets of decisions, and obviously the price value is not actually part of the budget. That's fine. In terms of broadening your knowledge and understanding of the use of the software, I have a budget range here, so all of these things add up to the same amount. But I could add a new group, a brand new group that changes sales price. This is sales price. And you can see it's now a separate part of the model. Now what will Evolver do if I give it multiple decision sections? change them all at the same time. It will enable me to have some parts of my business modeled as budgeting problems, other parts as recipe issues. There might be other grouping problems where I'm turning on or off different decisions, simple yes-no decisions, and so on. And Evolver will be able to solve all of those simultaneously. There isn't a limit in Evolver to how many of these things we can put in. But again, the idea being that, oh, hang on, we could actually do that. I don't need to just play with my budget level and then try and work out an optimal sales price. I might do them at the same time. It might be that the optimal solution is actually to have a high sales price, let my capacity for production be low enough, put money into advertising so that I sell this expensive product, which may sound familiar to most of us as consumers out there, where there's something that seems too expensive, but we all buy it anyway. You know, I happen to carry an iPhone with me. I'm probably an example of that type of sucker. However, it can be built in, and you guys can do that sort of optimization yourselves. I'll put that away. Pardon me. Let's look at another example. Again, something quite different. So we've had a budgeting dollar issue, had some transportation issue. Now I'm going to look at the actual physical placement of an asset. In this case, video towers. It's probably better in the modern world to call this example location of mobile phone stacks, but anyway, we've got here an issue where I have 3 towers, or I have the capacity to build 3 towers. 1 large, 1 medium, and 1 small. Each of these can be placed anywhere on the grid. They all have a different capacity to reach an audience. And I have these different towns, from Alma to Auburn, down to Greenwich, Carthage in the middle, and so on. Each of the townships has a location and the population itself. I want to place my fixed number of assets in a particular location or locations such that I maximize the total number of listeners. Okay? Now, this model is a little bit difficult to see on the spreadsheet, but I'll create a graph for you shortly to help make it easier to understand. But the basic idea is that each of these cities has a location, and this functionality will determine whether or not the distance between any of the 3 towers and the city is less than or equal to the range of each tower, and if so, then it's got coverage. So I have total population as influenced by the tower. So let's minimize our listeners. Before I do that, I'll go and throw a little chart in. Makes it easy for us to see. So I want my chart to... I'm having trouble with my chart. I'm just being too big with the click, so let's just cut that. See if I can start again. Okay, one more time. Simple scatter plot. As you can see, it's taking a while for Excel to catch up. This is just Excel functionality here. There we go. Select some data. So the tower will have these. Towers will have these as X coordinates, and these as Y coordinates. So there's the location of my 3 towers on the graph. And then I'll also add the towns, who have X coordinates and Y coordinates like this. The model, of course, will optimize without having to do that. However, it just looks a lot nicer to be able to see what's going on. So, what is Evolver going to do? Well, all we want to do is to maximize our audience, total number of listeners, could be total people covered by your mobile towers or whatever it might be, by moving the locations, XY coordinates of my 3 towers ABC to be somewhere on this grid from 0 to 60. But I'm being a bit more pragmatic about where exactly I can place these. So rather than saying it has to be in whole, say, kilometre blocks, if this value was a kilometre, or allowing it to go down to the nearest millimetre, I've said let's make this easier on Evolver and on ourselves, where I will only allow step sizes of 0.1. So that could be 100 metre blocks. So each, the location will always be only to 1 decimal place, severely reducing the number of possible combinations that Excel needs to, that Evolver will attempt, and therefore it will get us to a solution far more rapidly. And there's no reason necessarily to let this range across any value for the actual location. Much easier to think of this in terms of discrete jumps. So maybe that's 100 meter jumps. Again, no other constraints because they're all built into, well, the towers that go somewhere in here. Click OK. Oh, just to confirm once again, this is a recipe problem because these values can all be changed independently. They don't have to add up to anything. They're not being chosen out of particular groups. Just give me those numbers. So changing these 6 values to try and get my model to be optimized. So I'll start this again. And what's fun is showing every try. So what's started here is the Evolver is all these different combinations where to put the towers, not randomly, trying these things intelligently, seeing what's better and what doesn't. Now, what's on the screen, hopefully that refreshes enough to see the screen, graph up there, is every trial, as opposed to every new best trial. So the best solution is currently at nearly 70,000. So 68,000 on here. And we started at 38. So not by changing the power of the station or anything, like simply changing a location, I've improved my total coverage of almost double. 38 up to 6. And that's only in 1 minute to run, and it's only 6 trials. After a minute, Evolver, if I was actually run through a webcam, a webinar, would be many times magnitude so quicker than that. I'm going to let it run for a little bit, I think there was a solution here, although you can see how much improvement we've actually achieved. Where's it going? It's on screen here. Let's look at my track. Yeah. Quick improvements neat, and it's leveled for a while. The last 100 or so trials, it hasn't found something better. That might indicate the are our optimal solution, or that it's actually going to find a better one. And sure enough, it's suddenly an idea that is much better. So we went from below 70 to now above 1,000 lists. Okay. So you think about, I've got fixed assets here, but by simply making a smart decision, I've nearly tripled, they're more than doubled my order, than doubled some outcomes important to me. And this is real power of optimization. We're talking about every business is attempting to optimize. 2 businesses are actually doing quantitative optimization. They're just hoping that they're doing, or they've done in the past, or based on gut feel, that their decisions now are actually the best ones. But you can see the sorts of drastic improvements that can be made when you use optimization. It can be difficult to come up with this model interface, and just as a quick plug, Palisade also provide services to enable you to do that model build in the first place. The software itself, as you've seen, is very simple to use. There are some better and worse ways of using software, which we'll explore in the next 2 webcasts in more detail. But you can see how much scope improvement there can be in almost any type of business. So I'll stop that now. I'm quite happy with 80,000 listeners compared to the 38 or so that I started with. Click OK. And now there is my optimal mix. So I have, there is C, B, and A. So little tower C gets a couple of things here, B and A. 2 towns have still been missed. Maybe there's a solution where those can be picked up. We need to run this for longer to find out. But for now, we've got a drastic improvement over what we started with. So I'll put that one away. Now I'm going to look at an example called advertising selection. Again, it's about pardon me, spending an amount of money. It does involve budgeting, but we're not going to use the budget method. I'll quickly go to my model definition. What's been built in here is actually a recipe problem. So here the decision is not a financial one. The decision is the number of ads of different types, TV, magazine, newspaper, radio, direct mail, probably should be updated. This is actually Facebook advertising, you know, promoted tweets and so on. You know, what kids these days are doing. But my decisions don't have to add up to something. This is a total of 20 ads, but these decisions won't always add up to 20. I have an overall budget of 50,000, which I don't want to exceed, but my decisions don't add up to a certain value. Therefore, it's a recipe problem. Now, this advertising blend example is actually an application used by one of our customers that's a large FMCG, and they exactly look at that. What is the best use of their advertising dollar to try and reach the most number of people or a particular demographic? Obviously, the models could be more complicated than what you're seeing here. So we're trying to maximize our audience by not spending more than our money. So what's the best allocation for the number of ads that we purchase across these 5 media? Well, there are a couple of tricks involved here. Firstly, it's not just a matter of putting all of our efforts into the one that seems to get the best audience per ad, because TV and magazine, which initially look dear, they get cheaper the more I spend on those. So I get a bulk discount there. Likewise, the business has simply decided that we must spend more on TV advertising than radio advertising. Seems like a strange thing, but there we have it. That's what they want. Okay? It's also been determined that we will have at least 2 ads of any type. We're not going to ignore any one of these media, and no more than 20 of each type. So this is an example of non-actual or non-physical or logical limits being used as constraints in the model. These can be arbitrary business decisions. Go to my model definition, and I see that I have my 2 and 20 limitations on the number of ads that I'm going to use, and these are all integers. Obviously, I can't purchase half an ad. I have this odd constraint that I need to spend more on TV than radio. And then my budget is simply that the total cost of whatever the ad mix is that I pick has to be less than 50,000. It can be a lot less, it doesn't matter, but it can't exceed that. So let's start this model and see if we can improve on our total audience of 112,000. Obviously, a loaded question because I know we can. But while we're looking at this model solving, it's just getting started. Now, there are both trials and a certain number of them are valid. Now, because we have constraints external to our decisions, Evolver might try something. It says, look, this will be a really great solution. It really increase our audience level. It tries it, but then it violates either the budget constraint or the needs to big radio constraint. That would be the invalid trial. At the moment, it's about 50-50. So half the time it tries something new, it's invalid. I can see I've got 31 at the moment, valid solutions, 32 valid solutions. They're the solutions that don't violate these additional things that I included in the model. I'm now up from 12,000 audience to over 130,000. One's quite good, so I wouldn't expect to die off just yet. Let's look to improve 134,000, and eventually we'll take her off. So that's validity. There's nothing wrong with that. It's just letting us know that in this case, now at about a third, so a third of the attempt that it makes at providing a better solution actually turn out to be valid. So it's much easier to violate the constraints I put in than to include them. A few more options that we have here we're matching. What included here is, of course, showing a log of our progress. We started at a certain point, 20 trials we improved, 21 trials we improved, then the 42nd trial improvement, so on. And the last, our 99th trial was the last improvement made. So we're now to, we're just about to crack 200 trials. Seems to have tapered off, 134. So I'm just going to leave that there. There's probably, or there are potentially more gains to be made, but I'll leave it at that. Click yes. So now, without exceeding my budget, and in fact spending exactly all of my budget, which as you know is always better than leaving some cash left over, with this mix of ads, so doubling the magazine, doubling the initial radio spend, but leaving everything else the same, I've now reached an audience of 134,000. Obviously a big improvement over the 112 that I had to begin with. Now, what if I look at this in a different way? Most of this, the topic of optimization is really around the artistry in producing this model. But part of that artistry is understanding the sorts of things that are possible. It's quite difficult to just come up with this inspiration out of nothing. So I'm going to show you another way of looking at this same problem, and maybe these words will resonate more than, let's maximize the audience for these amount of dollars. What if management said we'd be happy with 125,000 as our audience? More is better, but 125 is satisfactory. So how can I achieve 125,000 for the least amount of money? Okay, so this is no longer a maximization problem. It's going to be a minimization problem. So I haven't really built a model for you. Let's do this now. I want to not maximize anything. I'm going to minimize my total cost. Minimizing cost is always a good thing. I will minimize my cost by changing my advertising spend or allocations. Yep. However, if I'm minimizing my cost, I no longer have this issue about budget, because obviously it's going to drop it down from 50,000 if it can. So I'll delete that. However, what I do want to do is add a constraint. And for this constraint, it will be our min acceptable audience. Oh. Minimum acceptable audience. And for that, I need my total audience to be bigger than or equal to 125,000. And I've got no need for an upper limit, so I just get rid of that. So as long as my audience remains bigger than 125,000, that's all good. Let's just do this as cheaply as we can. Click OK. So now it should make changes here that will actually reduce the total audience to acceptable levels, but tell me what's the least I could spend to achieve that. Let's see how that works out. Okay, so that's good now using spending money. Not much just yet, improvements we found, because it's still actually reaching more people than I care about. So now we're finally 125,000. I know that one goes on this, but we'll try to find a way of hitting that audience total, maybe a tiny more, reducing rate. I made up to 42,000. So maybe someone said, look, 50 million, you're going to get me the biggest audience you can. And that was about 134 or so thousand people. But the question is, oh, look, 125 would be good enough. How much do we spend now? Well, I can save $7.2 million and still hit a reasonable audience level. Okay, so stop that there. But just to show you, we can look at problems in different ways. And also, as you can see just on the screen, it's super quick and easy to actually use the software itself. The implementation is just point and click interface. Very, very simple. Okay. Now, there's a few examples of both budget and recipe problems. We're getting close to the end of our hour here, so I just want to show you a couple of slightly bigger problems, get you an idea of what we can do with some larger things. So this problem, very small. All of the ones we've seen so far quite small. Let's look at something a little bit bigger. So we saw the transportation problem before. Let's look at a much larger one. So as this describes here, logistics models can be very large. We have a simple issue about going from manufacturing sites to retail sites, minimizing the cost, meeting retailer demands, not exceeding manufacturer capacities. Okay, so it's a linear programming problem. However, the number of cells that can be changed here, even though this model is very small, it still exceeds your basic solver capabilities. So here I have 10 manufacturers trying to ship goods to 25 retailers. I have the capacity for each manufacturer. This obviously can't be violated. And I have the demand from each retailer. And this probably shouldn't be violated. Here I have the really tricky part, which is this is, if you like, the matrix of cost coefficients to go from each manufacturer to each retailer. could be, generally be based on distance. How far will it take, or how much will it cost to get things from manufacturer 10 to retailer 7? Well, that's $320. Okay. Now, at the moment, my total cost is 0, which sounds very good until you realize that all of my constraints here are being violated. So what I need is a solution to this problem where I actually don't violate these 25 constraints along here. I don't violate these 10 constraints here, but I also happen to minimize my total cost. If I just look at that model definition, I see that I have a big recipe issue, or recipe solving type, where these cells need to take values. Put them in as any. They could also go in as, it could be an integer problem. That's fine. I have demand and capacity constraints. Let's just solve this one as is. So as you can see, evolve is initializing. Fortunately, I have to wait for this. This problem itself, being a linear programming problem, the optimization will actually solve very rapidly. The other optimizations, we saw that they ran, and we waited for them to start tapering off in terms of how much more improvement there was and so on. Linear programming is very straightforward. So you can see solutions being put on the spreadsheet, and it's solved already. So although, because of the issue about going through the webinar, it's gone a bit slower, you can see how almost immediately this problem is solved. So manufacturer 9, for example, sends 200 units to retailer 1, 100 to retailer 6, and that's it for a total of 300. Obviously, none of the capacity constraints are violated. There's a little bit of slack here at manufacturer 10, but we didn't need them. Also, all of my retailers are getting the demand that they wanted. No problem, and the total cost is 500,000. This is the best solution. And there was no way that I was going to be able to do this off the top of my head to determine who needed to send what where. I'll put that away. I'll quickly show one more problem, again, it's of a slightly larger scale. This is a work scheduling issue. So we have constraints about when the company's open from 7 a.m. to 11 p.m. Guessing it might be a bit of a throwback to the old 7-Eleven days, before obviously they went 24-hour. So we've got a model constructed where we need to get people to start their shift at a certain time on certain days. There are rules about when they can be on and so on, like obviously you can't work all 7 days in a row, that type of thing. There are going to be breaks that they get, and therefore the total number of workers available across all of these time periods. And what we want is to meet minimum employee requirements. We think we need this many people, perhaps to achieve a certain service level in each of these days and hourly time periods. So what is the fewest number of employees, and when do we also put them on, that actually generates this, meets this requirement. So I could put on 100 people in every session, and sure enough we'd satisfy things, but then the total number of employees would be too high. The current solution you're looking at, just like some previous examples, is not actually feasible. Despite what maybe some people in accounts would tell you, you can't simply not employ anyone and hope the business still runs well. So here we have between 0 and 20 whole people being employed to start their shifts in this block of time that then feeds through into the model to determine when people are on, when they're taking their breaks and so on, and therefore who is or how many people are available in each time period. Then we also have our grid down the bottom where these requirements need to be met by the total number of people available at any of those time periods. So I'll just run this one. Once again, just like the previous poll, we're going to have to wait a little while for it to set itself up. It's okay. What I'll do is I'll take this opportunity to talk about what we're going to do in the upcoming months. As I mentioned a couple of weeks ago, our DTS webcast, we'll be doing these a month, and this was the first in a sequence of 3 optimization webcasts that we had. So this week we started looking at Evolve, so getting your hands a bit dirty, a bit wet, if you will, on optimization and optimization spreadsheet using this cool tool. In our second Evolve webcast, I'm going to look some more, not necessarily obscure, but some different types of optimization problems, like grouping, scheduling, and so on. We'll look at how these things work. Also take a little bit more of an in-depth look into the actual way or better ways of using Evolver itself. Like most pieces of software, there are good and bad ways of using it. So some of our clients have found unbearably long runtimes. But they hadn't set the model up in a fit way to begin with, and so we're always going to be stuck in that to make a few changes. Some models are being solved within minutes, and also getting solutions. Okay, look at a bit more in-depth into the software and that kind of things. Then in our third optimization webcast, we're actually going to introduce Risk Optimizer. Some of you may have been looking at the modeling so far and noticed that there's no uncertainty. There are no at-risk functions on this spreadsheet. There are no log normal distributions, no binomials. There's just no uncertainty in there. It doesn't make the optimization invalid. It just means that it doesn't have as hard and a sum around uncertainty. So in the third webcast, we're going to look at actually optimizing uncertain models, which, as you might imagine, involve combined evolver and at-risk. So running a simulation as well as using the optimization algorithms that we have here. Those two things combined are essentially called Risk Optimizer, which is an example, also an option in at-risk industrial, or the DecisionTools Suite industrial. You may have seen it in the ribbon when looking at at-risk. Pardon me, you've got industrial edition, and this is quite simply our optimization under uncertainty engine. So that's what we're going to do. I want to end by showing you this model being solved. Still preparing my constraints. Give it a minute or two. That will then hopefully finish our webcast high note. As I mentioned, if you do have any questions, if you've written them down, I'm going to address them later for you, or you contact our office at any point, and we'll get back to answering those. Unfortunately, as I'm doing this during the class, I can't actually look at those. Now, unfortunately, this can actually start. It's a shame it doesn't seem to start. That's right. But I'll quickly see if I can get started. I would like to show you the final solution for this one. Okay, so I'll show my screen again. Just for those who don't know, the example spreadsheets are in the Evolver Help section. Looking at worker scheduling. And simply running that model. See how we go. If this doesn't work now, then I'll just end it, but I was hoping to be able to show you the solution to this one as well. Now, there's one more thing while we're looking at this. Some of you may think that these little models that we're looking at, where the profit suddenly increases dramatically or the costs suddenly reduce dramatically, that in fact we've artificially set these up and you wouldn't see any of these sorts of results realistically. And the answer is simply that's not true. Oh, good, this is starting, that's great. I have worked with clients, like genuine real-world bricks-and-mortar clients, where we have literally saved tens, if not hundreds of millions of dollars because, for example, we're able to better run the logistics of the business and not require extra equipment or land to be purchased. That's a very good example of one. We're also able to optimize portfolios in ways that were previously inconceivable in terms of the capacity to both increase expected gains but also limit the volatility. So maybe your company won't go from minus 2 million to plus 12 million necessarily, but you should actually expect there to be very big improvements that are made. So here my model is solved, as you saw, very rapidly. All of my constraints have been met in terms of the number of people that are required as a minimum, and here are the people that I need to put on and get their shifts to start at which times on which days. Easy. Takes breaks into account and so on. Okay. So I'm glad I got that to work for you. That was Evolver Part 1. Please tune in a couple of weeks again for Evolver Part 2, and then also our risk optimization that will come soon after that. There'll be emails and so on about, or our website will be a good place to look those things up. As I said, any questions, we'll try and get back to you in the next few days. Otherwise, I hope you enjoyed this, and I hope to see you guys on our webcast again in the future. Thanks and have a good day.